Okie doke. Good morning. Today we're going to start off talking about real gases. So we've talked about all this, ideal gas law stuff, but it turns out that most gases are not ideal. And so let's go ahead and take a look at some conditions that would, make gases more real. So if we look back at a number of the assumptions we've made, way back when we started talking about gases, one of those was that gases, molecules don't interact. And so that assumption is not quite true. Unfortunately, we're going to see next chapter that everything will be able to attract other, atoms or molecules. So this is an assumption that is simply not true. However, this is a problem at low temperatures. So if we're at higher temperatures, we're going to see that this becomes less and less of an issue. The reason for that is, so of course temperature is, it affects how fast things are moving. If things are moving really quickly, they're just not going to have time to interact with each other. They're just going to zip right past each other, and that's going to be the end of it. Any attractive force that would try and make them, slow down or something, it's just not going to happen because there's just not enough time as they zip by each other. So at high temperatures, gases behave a little bit more ideally, but at low temperatures, they tend to have problems. So that is one kind of area that we have that. And then we're going to see this is also a problem at high pressure for the same reason. Because high pressure means that these things are colliding frequently. Typically, they're also going to be colliding with each other, and the more they collide with each other, the more chances they have to interact. And so, for just by putting a lot of them in a small place, that's how we get high pressure. We're going to have problems with them interacting with each other. And so these are kind of the two major conditions that would lead to gases not behaving ideally. So if we have low temperature and high pressure, that's kind of the worst scenario for predicting a gas's behavior using the ideal gas law. And so we have one more thing. We kind of have different gases let's look at the temperature thing, actually. Not all gases are the same speed at a given temperature, right? We saw that, smaller gases would tend to have distributions that were faster. We're going to see that now we've kind of made that assumption that all gases behave the same way. We're going to see that higher molar masses lead to slower speeds, right? And we kind of made the assumption that the temperature would be proportional to the speed earlier. So we're going to see that higher molecular rate gases will have less ideal behavior. So we kind of have problems with conditions, and then we have also a problem with the identity of the gas. So we're going to see that a light gas at high temperature and low pressure is going to behave more ideally. So like hydrogen gas at 3000 Kelvin in a vacuum is going to be behaving the best in terms of our ideal behavior. But something like, sulfur hexafluoride at high pressure and low temperature would be completely the opposite case. So guess what? we have an equation to deal with this. Oops. Alright, so we have. Let me just write out this crazy equation because I'll explain it in a second. Okay. So we have to basically make some adjustments to our ideal gas law. This is the van der Waals equation, by the way. And we're going to see that these A and B are adjustments that are going to help kind of make our gases take into consideration some real behavior. So if we look at Discord real quick, where is Discord? Oh, it's here. Oh, we have some constants here. Let's take a look at these, and let's see if we can see any patterns between them. For example, why don't we look at the first 5 of them? What do we notice about the substances that are there, as well as those constant adjustments? What do we notice is happening as we change our gases here? Yes, that's absolutely right, Kevin. So as the molecular mass increases, we see that A and B also increase. So again, these are adjustments that are there to kind of help curb the effects of molar mass leading to different speeds. If we look at, why don't we look at nitrogen, oxygen, and fluorine now? What do we see about those 3? We see that's going down, right? Nitrogen has the highest value, oxygen has a lower value, and fluorine has an even lower value. But we know that fluorine is the heaviest of those. And so we also see that the size of the molecules does come into play as well. So nitrogen is a bigger molecule than fluorine is. And so we kind of make the assumption that molecules don't take up any space, so that the volume is going to be exactly equal to the container. But there are some small effects that different sized molecules will have as well. So we kind of have these constants here that van der Waals came up with to help predict gas behavior a bit more accurately. And so why don't we go ahead and do a comparison? We'll take a gas and we'll see, a few important things here. So let's see, which one shall we do? Let's do this first with the ideal gas law. And then let's use van der Waals equation. And let's compare them once we do that. Here, let's just make this easy for us. Let's just not even worry about this. Let's make it 25 moles. Just so we don't have to do that extra calculation. So if we use the ideal gas law, we would get 5 times our constant times the temperature over the volume. 0.08206 times 200. So we get a, wow, that's, oh, because I didn't type it properly. Okay, so that one is 16.4 atmospheres. All right, if we want to, I'm going to just copy the equation because it's complicated. If we want to solve this with van der Waals equation, let's go ahead and look up xenon. Awesome, I'm glad we got the same answer. Xenon here has an A value of 4.19. Oops. And B was equal to 0.0510. All right, so we have to do a bit more complicated math here. Thankfully, I guess I chose to have the moles and volume equal. That's going to make our lives a little bit easier. And V was 25 minus 25 times 0.0510 equals to 25 times all this stuff. Woof. Let's go ahead and solve this craziness. Okay, so this component here, I'm just going to do this stepwise. That's 410.3. 25 minus 25 times 0.0510. This is 23.725. I think we have 3 sig figs there. Okay, so now we can actually do this thing. So 410.3 divided by 23.725, subtract 4.19. Lo and behold, now all this calculation gets us to 13.1 atmospheres. So with the ideal gas law, we got 16. Making some adjustments for the identity of the gas, we get 13. This may not seem like a big difference to you, but this could be the dividing line between a tank that explodes or a tank that doesn't explode. So this would be more likely to be our real answer, the one that has the adjustments with it. So if this tank were to explode at 15 atmospheres or so, and someone is asking you how much gas can I put in here, if you were to use the ideal gas law, you would end up exploding your tank if you put in 25 moles of xenon. But it should actually be safe to store that amount in the tank at that temperature. Of course, it's probably not a good idea to be very close to the limit anyway, but that aside, we're going to see that our assumptions may lead to faulty answers. So it is better to accommodate the real behavior of the gas. So there we go. Kevin, did you also get 13.1 for this? Or someone else if they did it? Just to make sure that I'm doing my math properly. Okay, cool. Yeah, I know this one with all the pluses and minuses and squares and stuff, there's definitely a lot more algebra that's involved here. But yeah, so there's going to be just a few problems in your homework that deal with the ideal or real gases. So, but that's just something to learn. If you are going into a field that does work with gases, you're going to be using this equation much more than you would be using the ideal gas equation. So you'll have some homework problems on this. There's a couple that will basically ask you to compare as well between calculating for a real gas versus a ideal gas. Okay, so that would be our answer. Exciting. 25. Okay, is there anywhere we could have gone wrong here? So these two should definitely cancel out. I'll double check my math just in case as well. So 25 minus 25 times 0.051. Okay, I still get that. 25 times 0.08206 times 200. 410.3. Okay, divide that number by 23.725. Subtract 4.19. Okay, I got 13.1 again. Okay, oh, you did neon. Okay, so you used the wrong A and B. Well, that's interesting. Very interesting. So doing neon, you would get completely different answers, apparently. So, yeah. There we go. Okay, so there we go. So you'll have some practice on this. Just another equation for you guys. So with the adjustments, you get closer to real life behavior. And so this would be more useful for someone who's actually going to be using this in real life. Alrighty. So we're done with gases now. Hooray. We have 2 more chapters left in the semester, and we have about a month to go, which is pretty nice. So we have our exam next week, which is on Lewis structures and geometry and that sort of thing. And then after that, we're going to just we have solids and liquids, and that's it. So, exciting times. So do we have any questions on anything with gases that we'd like to go over? We do have a bit of time. And I guess, why don't we do your exam review tomorrow? Just so we don't have to meet on Thursday. Make it a little easier for ourselves. So if you have any homework questions or things you want to go over, let's do those tomorrow instead for you guys. We're going to start talking about the next chapter now, but for tomorrow we can go ahead and do our pre-exam review for your exam next week. And I think next week you're only going to have 1 day of lecture anyway because we have a holiday as well as your exam. So it's exciting. Okay. So I do not see any questions. So let's go ahead and move on. There's one part of chapter... What chapter are we even on now? Is this 10? Yeah, so chapter 9, when we talked about geometry. Yes, that will be the only homework this week for you guys. So there is one part I skipped over in chapter 9, I think it was, when we talked about geometry and all that sort of thing, which deals with polarity. Polarity is kind of a unequal charge distribution. And something like this would be our dear friend water. Would be an example of a polar molecule, and we're going to see why that is the case in a little bit. Actually, we can look at it right now. Why not? We know that O and H have very different electronegativities. Oxygen's is around 3.5, hydrogen's is around 2.1. We know that oxygen will kind of steal electron density. Because it's more electronegative, remember electronegativity is the tendency of an atom to kind of hoard electrons, to kind of gather electrons towards itself in a bond. So this tells us that while we kind of look at this Lewis structure and we say, okay, the bonds are shared, or the electrons are shared between oxygen and hydrogen, it's not a 50-50 sharing. We're going to see that there's actually more electron density on oxygen than on hydrogen, which gives it a partial negative charge. That's the Greek symbol delta, lowercase delta, which you may remember from calculus is partial. So partial derivative, same thing here. And as a result, our hydrogens are going to be partially positive. So this is an example of a polar bond. We have a hydrogen that is slightly positive, an oxygen that is slightly negative. These are not full charges, they're just partial charges. And so we can see that we're going to kind of have poles here. Just like a magnet has north poles and south poles, this bond has a negative pole and a positive pole, which is why it is called polar. The other hydrogen, of course, would also be slightly positive. We also can draw these. I'm going to just go ahead and draw this again down here. We can also draw this by drawing the dipole. So two poles, there's two of them. We draw kind of where the electrons are going. They're going towards oxygen. And we kind of draw this little plus part on the positive one. So we see the electrons are going towards oxygen away from hydrogen. These are what are called dipole moments. Actually, let's just call that the dipole. Let's not worry about making that more complicated. And for all of you who want to remember your vectors from math or physics or whatever, if we were to add these vectors together, we're going to get an overall vector that's going to be something like this. Right, we can see the vectors there in the top molecule. They're both pointing, up and towards each other. So remember, vectors have a horizontal component and a vertical component. Those two horizontally will cancel each other out. However, they're both pointing up, and those up parts will be summative. And so this tells us that the top half of this molecule overall is negative, partially, and overall the bottom half of this molecule, as drawn, is partially positive. So not only does water has polar bonds, but it is also a polar molecule. And that's going to have some implications for us. Let's look at those implications in a little bit. But first, let's kind of look at this idea of polarity again. So here, another molecule for us, carbon monoxide. If we put formal charges on it, by the way, we should get this. So if we do have formal charges, we can see very clearly that we have two poles here. This is a bad example. Why did I choose to do this one? That's not even got a kind of polarity. Let's do this one instead. Here's another molecule. We'll make this one a little easier for us. So we have no formal charges in this molecule. So if we want to go ahead and look at it, we'll see between carbon and oxygen, oxygen is more electronegative, right? Again, further to the right. So we would expect that we have a dipole that looks like this. We have a partial negative on oxygen, partial positive on carbon. Indeed. And we're also going to have the same thing going the other direction. However, these dipoles cancel out. Because they're pulling equally in the opposite directions. So the oxygen on the right is pulling electrons away from carbon. However, the oxygen on the left is also pulling electrons away from carbon. And so as a result, the electrons are not quite sure what to do. So they can't really go towards one of the oxygens because then the other oxygen is going to start pulling them back. So overall, there's going to be no change. And so these cancel out, making carbon dioxide non-polar. It does not have poles because those vectors cancel each other out. So we have one pointing to the left, one pointing to the right. They're of equal strength. And so, poof, it's gone. So this kind of idea of using the vectors will kind of let you know if something is polar or not as a molecule. So even though it has polar bonds. So each CO bond is polar. However, the entire molecule overall is not polar because those dipoles cancel out. So you kind of have two options here. You can either have completely, let's just write that, for a molecule to be nonpolar, you can either have no polar bonds or have all dipoles cancel out. Another way of describing this is symmetry. If your molecule is symmetrical, the dipoles should cancel out. We see that carbon dioxide is symmetrical. We have, anywhere we cut this molecule in half, the other half is going to be exactly the same. If we look at water, if we try and cut water in half, we see that we do not get the same thing, at least in one direction. So if your molecule is completely got radial symmetry where anywhere you cut it, it will all be the same. This water molecule, if we try and cut it horizontally, we're going to see we have two lone pairs on the top and two hydrogens on the bottom. A lone pair is not the same thing as a hydrogen. They are not symmetrical. So you'll not be able to cancel out your vectors there. So symmetry is kind of an easy way to think about whether a molecule is going to be polar or not. We typically have some kind of guidelines for whether a bond is going to be polar. If your change in electronegativity is between 0 and 0.4, that's usually a nonpolar bond. These are rough guidelines. It is going to be a spectrum, but these are kind of, rules of thumb, let's say. So if your difference in electronegativity between your two elements is between 0 and 0.4, again, this is the magnitude. We don't really care about sign here. Then it's going to be a nonpolar bond. If it is, let's make it over there. If we have 0.4 to about 1.9 or so, that is going to be a polar bond. And then if X is greater than 1.9, that's just an ionic bond, completely ionic. So if we looked at carbon and oxygen, carbon has an electronegativity of about 2.4. Oxygen is about 3.5, excuse me. So the change in the difference in electronegativity is 1.1. That's kind of smack dab in the middle of our polar bond range. If we look at carbon and hydrogen, however, I'm just giving you the numbers. Again, you don't ever need to memorize electronegativity values. They would be given to you in a question, or you would have some sort of chart that you could use with it. We see that the difference between carbon and hydrogen is 0.3, which we would expect to be a nonpolar bond. And so we would see that this molecule here, methane, should be nonpolar overall. All of the bonds in here are nonpolar, and it is also completely symmetrical. So it has both reasons to be nonpolar. So all bonds are nonpolar. And it is completely symmetrical. So for two reasons, it's nonpolar. However, if we throw in a chlorine, we know CH bonds are nonpolar. We just did that. Chlorine is 3.0. Carbon is 2.4. We're going to see that that's a difference of 0.6. That's going to tell us this is polar. So we're going to see that chlorine will have the slight negative. Carbon will therefore have the slight positive. We're going to be pulling electron density that way. About to sneeze. Excuse me. And so we can see here we only have one vector because the carbon and hydrogen nonpolar would not have a vector associated with it. This is clearly going to be a polar molecule. And we can just verify not all bonds are nonpolar. And it is also not symmetrical. If you want to see the symmetry, let's just try cutting the molecule in half. If you look at that, we have a chlorine on one side and not on the other side. It's not symmetrical. If we try cutting it another way, if we try cutting it like this, we get the same problem. We have a chlorine on one side and not on the other side. So this molecule is not going to be symmetrical, and so it's going to be polar. as a result. What about something like ethylene? What do we think about this one? Is this going to be polar or not? Yeah, it's this one should also be nonpolar, right? If we look at a C and C bond, C is 2.4. So if we do, of course, the carbon is the same. There's not going to be a difference in electronegativity. We also saw that CH bonds were nonpolar. We also have a completely symmetrical molecule, so this one should be nonpolar. And so the geometry becomes important. If we take a look at our carbon dioxide again, our geometry, which is linear, allows us to cancel out those vectors. Excuse me. If we did not use proper geometry, remember our vectors here look like this, and they canceled out. If this was our molecule, we would overall have a dipole that moved in that direction. And so the molecule on the right would be polar. Because the vectors would not cancel out, we would have asymmetry. We would see, okay, look, we have now something that's not symmetrical. However, if we try and cut this carbon dioxide in half, we're going to see we have the same thing on both sides, no matter where we cut it. If I can get rid of that, yeah. If we cut it like this way, it's all the same. If we cut it this way, it's all the same. If you cut it that way, it's all the same, no problem. That's the difference in electronegativity. So that's carbon minus carbon. So just illustrating that if you're bonding the same element together, you're always going to have a nonpolar bond. Right, because they would equally want to steal electrons from each other. So that's our difference in electronegativity. We did already do H earlier, so that's why I'm kind of forgetting it. So this would be our CH bond here, which is going to be 0.3. So that's why I've kind of zipped past it, as it were. Cool. How about our dear friend formaldehyde? What was it was 1.1, right? So for the bonds that we have here, it doesn't matter if it's a double bond or whatever, electron sharing would still be the same. All right, so if we look at this molecule, we have at least, we have a polar bond and two nonpolar bonds. So that's telling us right away we do not have that all bonds are nonpolar. But let's just double check. Do we have... Well, let's go ahead and draw our vector in. We can see that because CH is nonpolar, that will not have a vector. So again, with this molecule, we just have one vector, telling us we have negative and positive. But we can go ahead and cut it through. If we look, we have asymmetry here. If we cut it in this direction, we are not going to have a symmetrical molecule. You know, again, you want to check multiple directions. If we were to have cut it here, it would be symmetrical. But we have to make sure that we cut it in multiple spots just to make sure for our symmetry test. So because if we try and cut it this way, it's very clearly not symmetrical. And the fact that we have different things, again, tells us it's not symmetrical. All right, how about this one? Lewis structure. I'm giving you all the electronegativities again. Kevin's already on top of it. So that would be a polar bond between nitrogen and hydrogen. So we have polar bonds. Let's see if they all cancel out. So remember here, yes, we want to include our geometry. So we would probably want to redraw this. Using our tetrahedral geometry. We're going to see that nitrogen is going to be dragging in all this electron density from all the hydrogens. Overall, that's going to give us a direction this way. But we could also do our symmetry test. Remember, asymmetry is what we get polarity from. Something that is not symmetrical. So if we cut it this way, is it the same? We have 3 hydrogens on the bottom, 1 lone pair on the top. Those are not the same. This molecule is not symmetrical. You can try it, you know, always try multiple directions. In this one, it's probably going to be symmetrical, but we're going to see that as long as we have one, you know, plane that it's not symmetrical across, it's not going to be symmetrical overall. This is all stuff you deal with in more advanced inorganic chemistry. You have different ways of talking about these planes of symmetry and stuff. It's awful. So we have polar bonds, and we have asymmetry, which tells us this will be a polar molecule. Here's a hint, maybe. If you have lone pairs on your central atom, it will always be asymmetrical. Assuming you have more than one outer atom. But that's one way you'll be able to kind of cheat this. If you have a bent molecule with at least one polar bond, that will be a polar molecule. I'm so bad at spelling molecule. Same thing with trigonal pyramidal. And seesaw, and all of our other fun shapes. Anything that has a lone pair on it, and it also has a polar bond somewhere in there, you're going to have a polar molecule. So that's kind of a cheat way you can do. So if you have at least one polar bond and at least one lone pair, excuse me, that's always going to be a polar molecule. Exciting stuff. So it may behoove you, if you like, to go back and practice with some of these structures to help kind of determine if things are polar or not. You'll have homework on this at some point, of course, so no worries there. But let's see, what's the point? We already maybe have talked about way back when that polar things typically would dissolve in water, right? An important thing for chemistry. So that's why something like formaldehyde will dissolve in water. Um, and you'll be able to use it to preserve your little anatomical specimens for anatomy class. Um, but it's important for us to be able to predict when something is able to be soluble in one substance or another. For example, why your paint does not dissolve in water. It's suspended in toluene, which is a nonpolar solvent. So you have all sorts of different things happening, and polarity does have a lot of ramifications. But for our purposes in chapter 11, we can also see that polar things can interact with other polar things. For example, if we take what's a fun polar molecule? Okay, here's one. So, sulfur in this molecule is going to be our partially positive one. It is less electronegative than chlorine is, just from his periodic position on the periodic table, rather. We're going to see that if a second sulfur dichloride molecule comes along, we kind of have two options. That other molecule could come along like this, or it could come along like this. I'm just going to kind of omit the lone pairs for now, if that's okay with everyone, just to make it a little bit more clear. So which one of these two do you think would be the better way for two of these molecules to interact? The one on the left or the one on the right? Yeah, I like that one as well. If we just go ahead and look at the charges, partial charges rather, it's better to have this partial positive interacting with the partial negative. These ones are going to want to repel each other a little bit. However, we're going to get a nice interaction between the sulfur of one molecule and the chlorine of another molecule. And these are what are called intermolecular forces. So remember, that means between molecules. And so in this case, this one is a dipole interaction. So we have the partial positive from one molecule interacting with the partial negative of another molecule. What do we think in terms of strength of this? Do you think this is going to be stronger or weaker than intramolecular bonds? That would be like covalent bonds or ionic bonds. What do we think is the strength of this? Is this going to be stronger than a covalent bond or an ionic bond, or is it going to be weaker do we think? Okay, that's true, Kevin. But well, I mean that's actually that would work. But I was also looking for just the fact that these charges are not quite full, for example, also. So remember, an attractive force. I believe we did this equation. Uh, maybe. Right, so some sort of attractive force follows this kind of idea, this equation. So we're going to see, because these are partial charges that, as you have noted, Kevin, are farther apart, this is going to be a weaker interaction. So small charges with relatively far apart molecules, let's say atoms, that's going to equal a relatively it's going to be a small or weak force. I'm sure you've seen some sort of equation like this in physics. For example, with gravity, it's the same thing, but instead, since gravity isn't charges attracting each other, it's masses attracting each other. So that's the force of attraction due to gravity. This is force of attraction due to charge that we're going to see here. So because these are partial charges and they are far apart because they're in different molecules, these are going to be small and weak interactions compared to intramolecular forces. So intermolecular is always going to be much weaker than intramolecular. No. Yeah. Remember, this is within a molecule. This is between a molecule. So we're going to see, the atoms within a molecule are already bound to each other. They're very attracted to each other, whether that's sharing electrons or full charges. These intermolecular forces are going to be weak interactions by comparison, because they are partial charges, for dipoles at least, and they are going to be within things that are further apart than plain old regular atoms. So let's go ahead and look at some more examples here. We have a special case with water and other similar molecules. We're going to see that water can make very nice kind of dipole-dipole interactions. And these are actually going to be kind of extra special for two reasons. Not only oxygen is much more electronegative than hydrogen, which means that the partial charges are bigger, and hydrogen is very, very small. Remember, hydrogen is one of our smallest atoms, and so for this reason, one water molecule can actually get up pretty close to another water molecule. And we're going to have a relatively strong interaction between them. So again, noting, this means a bigger Q and a smaller radius, a smaller distance between them. if we go ahead and just look at our general equation here, if Q goes up and R goes down, that means the force will go up. And so we're going to see we have a special type of interaction called a hydrogen bond. This is stronger than typical dipole-dipole interaction for the reasons that hydrogen is very small and the difference in electronegativity is pretty big, so the charges get a little bit bigger. And we're going to see this can occur when we have, yes, these are between molecules, yes. When we have hydrogen bound to one of these three elements in a molecule, those three elements, notice, are our most electronegative elements, fluorine being the most electronegative, and then oxygen and then nitrogen. Because those are going to be our most electronegative, we're going to have the biggest partial charges. And hydrogen being super small, again, is going to allow these things to get really close together. And so we're going to see that hydrogen bonding is a kind of special case of dipole-dipole interaction, where we have hydrogen bound to a very electronegative atom that can attract other similar atoms, or molecules, I'm sorry. So for example, we're going to see that this can bond with another HF. These kind of dotted ones here would be our hydrogen bonds. And that's where we have kind of these interactions happening. So in the above one, that's these kind of blue dots I've drawn, where we have hydrogen bonds that are taking place between our electronegative atom and then hydrogen with other molecules that also have this electronegative atom with the hydrogen. And so we're going to see that in proteins, this is going to be a super, super, super very important factor because proteins have a lot of oxygens and a lot of nitrogens in them, and those ones that have hydrogens on them can hydrogen bond with each other, and that's going to have a lot of ramifications. It's the whole reason that all of this stuff can exist is due to hydrogen bonding. It's very exciting. All right, so we are out of time for today. Tomorrow we will do our exam review. Monday will be your exam. I believe Tuesday's a holiday. Let me find out. Let me check your syllabus real quick. By the way, I did put the lab project guidelines and all that in Canvas. Okay, so it looks like your exam is on the 9th, Monday. Tuesday we will we'll have class. Wednesday is a holiday. So that'll be next week for us. So tomorrow, review. Monday is exam. Tuesday is we could even do our post review, or we could continue doing the intermolecular forces. We'll see. And then Wednesday is a holiday, so there will be no class on Wednesday. No, these are not included. Neither is the gas stuff. So your stuff for The exam is going to be on your, Lewis structures, the geometry, the molecular orbitals, the hybridization, the VSEPR stuff. That's your stuff on your exam. Okay? So not gases, not these intermolecular forces. Alrighty. I'll see you all tomorrow. Alrighty. I hope this is relating to the one that you did earlier. So yeah, double check. If it's wrong, let me know, but I think the answer made sense, but double check. Okay. See you guys.